In this video, I will discuss another important data structure called queue. The notation of a queue in computer science is the same as the notation of the queue in which you are accustomed to. There are queues of customers in a bank or in a grocery store and queues of cars waiting to pass through toll booth. The general rule to process elements in a queue is that the customer at the front of the queue is served next, and when a new customer arrives, he or she stands at the end of the queue. That is, a queue is a first in, first out data structure, or FIFO. Queues have numerous applications in computer science. Whenever a system is modeled on the first in, first out principle, queues are used. At the end of this video, we will discuss one of the most widely used applications of queues, which is computer simulation. First, however, we need to develop the tools necessary to implement a queue. The next few minutes of this video discusses how to design classes to implement queues as an abstract data type. A queue is a set of elements of the same type in which the elements are added at one end, called the back or rear, and deleted from the other end, called the front. For example, consider a line of customers in a bank, wherein the customers are waiting to withdraw or deposit money or to conduct some other business. Each new customer gets in the line at the rear, and whenever a teller is ready for a new customer, the customer at the front of the line is served. The rear of the queue is accessed whenever a new element is added to the queue, and the front of the queue is accessed whenever an element is deleted from the queue. As in the stack, the middle elements of the queue are inaccessible, even if the queue elements are stored in an array. So we can define queue as a data structure in which the elements are added at one end, called the rear, and deleted from the other end, called the front, a first in, first out, or FIFO data structure. From the definition of the queues, we see that the two key operations are add and delete. We call the add operation add queue and the delete operation delete queue. Because elements can be neither deleted from an empty queue nor added to a full queue, we need two more operations to successfully implement the add queue and delete queue. Those operations are isEmptyQueue, which checks whether the queue is empty, and isFullQueue, which checks whether a queue is full. We also need an operation called Initialize Queue to initialize the queue to an empty state. Moreover, to retrieve the first and last elements of queue, we include the operations front and back. And finally, we're going to use delete queue, which removes the front element of the queue. Input to this operation consists of the queue. Prior to this operation, the queue must exist and must not be empty. As in the case of a stack, a queue can be stored in an array or in a linked-in structure. We will consider both implementations in this video. Because elements are added at one end and removed from the other end, we need two pointers to keep track of the front and rear of the queue, which we call them queue front and queue rear. Now let's review how the class queueADT will define the operations as an abstract data type. So basically, the template class starts with public members. A boolean is empty queue, as we discussed, which is the function to determine whether the queue is empty. The post conditions for this function is it's going to return true if the queue is empty, otherwise returns false. Then we have the virtual boolean function of isFullQueue, which this function will be determining whether the queue is full or not. The post condition of this function is returning true if the queue is full, and otherwise returning the false. Then we use Initialize Queue, which is the function to initialize the queue to an empty state, and the post condition is we have to make sure the queue is empty. Next in the row is basically the virtual front, which is the function to return the first element of the queue. The precondition to that is the queue exists and is not empty, The post condition is if the queue is empty, the program terminates, otherwise the first element of the queue is returned. Then we have the back function, which is a function to return the last element of the queue. The precondition is the queue exists and is not empty. The post condition is if the queue is empty, the program terminates. Otherwise, the last element of the queue is returned. Then we have the add queue, which we're going to pass the queue element pointer to it. This is the function to add queue element to the queue. The precondition is the queue exists and is not full. The post condition is the queue is changed and the queue element is added to the queue. And finally, we have the delete queue, which is the function to remove the first element of the queue. The precondition is the queue exists and is not empty. The post condition is the queue is changed and the first element is removed from the queue. Before giving the definition of the class to implement a queue as an ADT, we need to decide how many member variables are needed to implement the queue. Of course, we need an array to store queue elements. The variable queueFront and queueRear to keep track of the first and last elements of the queue, and the variable maxQueueSize to specify the maximum size of the queue. Thus, we need at least 4 member variables whenever we want to implement a queue as an array. Also, before writing the algorithm to implement the queue operations, we need to decide how to use queueFront and queueRear to access the queue elements. How do queueFront and queueRear indicate that the queue is empty or full? Suppose that queueFront gives the index of the first element of the queue, and queueReader gives the index of the last element of the queue. To add an element to the queue, first we advance queueRear to the next array position, and then we add the element that queueReader is pointing to. Same way, to delete an element from the queue, first we retrieve the elements that queueFront is pointing to, and then we advance queueFront to the next element of the queue. Thus, the queueFront changes after each delete queue operation, and queueRear changes after each add queue operation. Now let's see what happens when queueFront changes after a delete queue operation and queueRear changes after an add queue operation. Assume that the array to hold the queue elements is of size 100, as you see on this slide. Initially, the queue is empty. After the operation add queue, queue A or something to the queue, the array is shown as you can see over here. If we do 2 more add queue operations and add B and C to it, like this case, then the queueFront is going to stay at 0 and the queueRear is going to point to C. So again, remember, in this case, we added A, B, and C to the queue, right? So now, consider a delete queue operation. Let's say we just run the delete queue operation. After this operation, the array containing the queue is as shown in this figure over here. The question is, will this queue design work? Suppose A stands for adding, that is add queue, an element to the queue, and D stands for deleting, that is delete queue, an element from the queue. Now, let's consider a sequence as this: AAA, DA, 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 and DA. So again, A stands for adding an element to the queue, and D stands for deleting an element from queue. This sequence of operations would eventually set the index queueRear to point to the last array position, giving the impression that the queue is full. However, the queue has only 2 or 3 elements, and the front of the array is empty, as you can see here in figure 1729. One solution to this problem is that when Q overflows to rear, that is Q rear points to the last array position, we can check the value of the index Q front. If the value of Q front indicates that there is room in the front of the array, then when Q rear gets to the last array position, we can slide all of the Q elements towards the first array position. This solution is actually a very good solution if the size of the queue is not that large. If the size of the queue is large, the execution of this solution may be very slow. Another solution to this problem is to assume that the array is circular. That is, the first array position immediately follows the last array position. We will consider the array containing the queue to be circular. So it is, even though we will draw the figures of the array holding the queue elements as before. As you can see, we're going to draw them like this, but we're going to consider they look like this, okay? That's just for the simplicity. Now, suppose we have the queues as shown in these two figures, okay? What you can see is in figure A, after operation add Q, QZ, what happens is the Q is going to turn into figure B. So because we are towards the end of the array and we said it's circular, so the next logical step, the next logical available place is going to be here, and that's why the Z is getting added over there. So, and that's all because the array containing the Q is circular, right? So now let's think about how we can actually find the next array position. Because the array containing the Q is circular, we can use the following statement to advance Q rear or Q front to the next array position, and that is Q rear equals Q rear plus 1% max Q size. If Q rear is less than max Q size minus 1, then Q rear plus 1 is going to be less than or equal to the max Q size minus 1. So the Q rear plus 1% max Q size equals Q rear plus 1 actually. If Q rear is equal to max size minus 1, that is when the Q rear points to the last array position, then Q rear plus 1 will be equal to max Q size. So Q rear plus 1% max Q size will be equal to 0. In this case, Q rear will be set to 0, which is the first array position. It's a very smart solution to just simply get the position based on when the current position of the Q rear is. This queue design seems to work well. However, before we write the algorithms to implement the queue operations, let's consider two new cases. In the first case, suppose that after certain operation, the array containing the queue is as you can see in the 1732-A. So basically the queue front is at 98 and the queue rear is at 98. If we do apply the operation delete queue, the resulting array is going to be what you see over here. So the queue front will be 99. Remember, we just deleted something from the queue, so the front is going to move to 90 from 98 to 99, and the queue rear is going to be 98. Now let's look at case 2. Let us consider that we have a queue shown here in 1733A. If we apply operation add Q and add Z, the result will be what you see over here. The Q front remains 99, and the Q rear, as you can guess, is going to be next, so it's going to go up to 98 from 97, and Z is going to get added over here. The array in this figure is actually identical. Let me go back one slide to the array in this figure. Just notice in the case 1, we had 99 and 98, And right over here, in case 2, we still have 99 and 98, which actually are identical. However, the resulting array in the previous slide, let me just go back there, actually represents an empty queue, whereas the resulting array over here is presenting a queue which is full. This latest queue design has brought up another problem of distinguishing between an empty and a full queue. So when you go circular, you solve the first problem, but then you introduce the new problem, which is you cannot figure out if this array is full or if this array is not full. However, good news is this problem has several solutions. One solution is to keep a count. In addition to member variables queueFront and queueRear, we need another variable count to implement the queue. The value of count is incremented whenever a new element is added to the queue and is decremented whenever an element is removed from the queue. In this case, the function Initialize Queue initializes count to 0. This solution is very useful if the user of the queue frequently needs to know the number of elements in the queue. There is also another solution, and that is to let queueFront indicate the index of the array position preceding the first element of the queue, rather than the index of the actual first element itself. In this case, assuming queueRear still indicates the index of the last element of the queue is empty if queueFront equals queueRear. In this solution, the slot indicated by the index queueFront, that is actually the last preceding the first true elements, is reserved. The queue will be full if the next available space is the spatial reserved slot indicated by queueFront. Finally, because the array position indicated by queueFront is to be kept empty, if the array size is, say, 100, then 99 elements can be stored in the queue. Looking at this slide, you will see we always are pointing to the reserved slot, which is actually right after the elements available to be filled up. So if you look at it, every time we add something, the reserved slot is going to move on. So when it reaches to 99, basically it is going to be telling us the queue is full. So we always have one slot being reserved and empty. So again, as I said, if the size is 100, then you only can have 99 elements because of that reserved slot. Now we're ready to start implementing the queues using the first solution, which is we use the variable count to indicate whether the queue is empty or full. Let's take a look at some code then. This class actually implements the functions of the abstract class queueADT, which should have been defined prior to the hand. So remember, because the arrays can be allocated dynamically, we will leave it for the user to specify the size of the array to implement the queue. And like before, what we're going to do is we're going to consider the default size as 100. So let's go through the functions one by one. So we have the operator assignment overloading, which we need to overload the assignment operator here. Then we have the isEmptyQueue, which is the function to determine whether the queue is empty or not. And the post condition is it's going to return true if the queue is empty, otherwise returns false. Then we have the isFullQueue, which is the function to determine whether the queue is full. The post condition to it is return true if the queue is full, and otherwise it's going to return false. Then we have the Initialize Queue, which is the function to initialize the queue to an empty state. The post condition is the queue is empty. Then we have two types, front and back functions, which this function returns front, this function returns back. The precondition for front is the queue exists and it's not empty, otherwise we don't have front. The post condition is if the queue is empty, the program terminates, otherwise the first element of the queue is returned. Then we have the back, which is the function to return the last element of the queue. The post condition is the queue exists and is not empty. And the post condition is if the queue is empty, the program terminates, otherwise the last element of the queue is returned. We have the add queue, which is the function to add queue elements to the queue. The precondition for that is the queue should exist and be not full. The post condition is the queue is changed and the queue element is added to the queue. Then we have the delete queue, which is the function to remove the first element of the queue. The precondition to it is the queue exists and is not empty, and the post condition is the queue is changed and the first element removed in the queue. Then we have the queue size, which we set it to 100 as a default, but remember it can be dynamically set by the user, which is the constructor over here. And then we have a copy constructor that we have to define. We have a destructor and the private members, as we discussed. We need a maximum queue size. To store the maximum queue size, we need a count, which is going to store the number of elements in the queue. We have the queue front, which is a pointer to point to the first element of the queue, a queue rear, which is the variable to point to the last element of the queue, and finally a pointer list, which is a pointer to the array that holds the queue elements. Okay, now let's talk about implementations a little bit. As discussed earlier, you remember that we said the queue is empty if the count equals 0. So understanding that, we can simply come here and ask this function to return that condition for us. So if the count, it should be like that. So if the count equals 0, we just want it to be returned, okay? Count 0 returned, and now we know if the queue is empty or not, as simple as that. Same way, if you remember, we can go ahead and check the queue fullness through checking if the count equals the maximum size of the queue. So this one could be implemented as simple as this. So if the count equals maximum size, then the queue is full. Therefore, we just ask this function to return the result of count equals maximum size back to us. So next one in the row is the initialize queue. So this operation initializes the queue to an empty space. The first element is added at the first array position. Therefore, we initialize queue front to 0, queue rear to max queue size -1, and count to 0 to complete this operation. So let's do that. So what I'm going to do is I'm going to come here to the initialize queue and add these 3 lines of code, okay? So set the queue front to 0, set the queue rear to maximum queue size -1, and then see the count is going to be set to 0. This means now we have a queue, which is basically just initialized to nothing. Next in the row is the operation front. So this operation returns the first element of the queue. So if the queue is non-empty, the element of the queue indicated by the index queue front is returned. Otherwise, the program should terminate. So because we want to make sure no error happens over here, what I'm going to do is I'm going to first assert and make sure if the queue is empty or not. And then what I do is I'll use the queue front as the index for the array and return that specific item. So the next operation in the row is going to be the back. This operation basically returns the last element of the queue. So if the queue is non-empty, the element of the queue indicated by the index queue rear is returned. Otherwise, the program should terminate. So again, what we're going to do here for the back is we're going to use an assert to make sure we're controlling the possible error. okay, to terminate the program there. And if there is no problem like that, then we return the list. This time the index of the array item is going to be Q rear, while over there for the front, if you remember, the index was Q front, and that comes from there. Okay, so the next one that we want to talk about is this gentleman over here, which is add Q, right? So we implement the add queue operation, and to do that, we understand because queue rear points to the last element of the queue. To add a new element to the queue, we first advance queue rear to the next array position, and then we're going to add the new element to the array position indicated by the queue rear. And this is going to be the implementation for that. So we check if the queue is full or not, and if the queue is not full, as you remember, we use the mod operator to advance the queue reader because our array is circular, as we discussed it before. So we implement that formula over here. We add one to the count, and the new element, whatever we want to add to the queue, is going to be set to the array element at the index of queue rear, and otherwise we can just produce some error messages to make sure user understands that an error has happened. So next in the row is going to be the delete queue, and the reason you see this error down here is because I left that produce some error message to you guys. So if you decide to do some type of function like initialize the queue or anything up there, or do whatever after else, that error is not going to show up. But I'm going to remove this code from here because I want to use this code as a reference in future. So just understand why that guy comes up, because this thing else over here needs something afterwards. So if I do this, or I add a line of code over there, you're going to get rid of that error and it's going to be clean. Okay, let me just put it back where it was. And now we want to go for the delete queue. To implement the delete queue operation, we access the index queue front. And because queue front points to the array position containing the first element of the queue, in order to remove the first queue element, we decrement count by 1 to advance queue front to the next queue element, so that the function delete queue is going to be like this. Let me just come here and add this guys to start implementing it. So the first thing that I need to check is if the queue is empty or not. And if it is not, what I'm going to do is, of course, I'm going to do count minus minus to get to the element. Okay. And then what I need to do is to set the queue front to be actually the queue front plus 1, right? Queue front plus 1. And then that's going to be modulus max queue size. As you remembered, we did this before. This is basically to advance the queue front because the array is circular, and we had the same thing up here when we did the function add queue. And basically, otherwise, we just need to produce some error messages, right? So else, do a cout or whatever. So what I'm going to leave here for you guys is just produce some error messages. Produce some error message, and there you go. And that's pretty much it. So now we arrived at the constructors and destructors. To complete the implementation of the queue operations, we really need to consider the implementations of constructor and the destructor. The constructor gets the max queue size from the user, set the variable max queue size to the value specified by the user, and creates an array of size max queue size. And if the user does not specify the queue size, the constructor uses the default value, which we set to be accepted as 100, and it's going to create an array of size 100. The constructor also initializes queue front and queue rear to indicate that the queue is empty. So now let's go ahead and do the code. So what I'm going to do here is first to check if the queue size is, let me just go for the queue size, is less than or equal to 0. So if something is there, and then what I'm going to do is a bunch of couts from the user. So you can basically do proper messages to user, something like size of the array to hold the queue must be positive. Please give me the size of the array, blah, 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 to get it from the user. And here I'm going to set the max size to 100. So I have my rules over there. And let's say the next thing is to check otherwise max size equals queue size. So at this point, I just let the queue size to be entered from user and max size be set with that if it is within the range, right? Which is going to set the max queue size to the queue size. Then the next thing that I need to do over here is actually set the queue front to be 0, as I just discussed why. And then the other thing that I need to do is to set the queue rear to max queue size -1. And the count should be set to 0 because there is nothing yet in there. And then I need to create a list, which is going to be a new from the type, whatever the type is, right? And the size of this is going to be maximum queue size. So again, while looking at the code, so you guys can see what I do, and let me just make sure this is right over there, correct? So what we do is we basically make sure this constructor gets the max queue size. So you're going to do the proper messaging over here, and of course at one point you possibly are going to have a cin, and you're going to get the max queue size in over there. But I didn't do that. I'm leaving the messages to you right now. I'll just set it to 100. So if the queue size is less than or equal to 0, we basically go ahead and put the maximum queue size to 100 because that's the default value. Otherwise, we get it from user, set it up as user wants, and move from there. Okay. The array to store the queue element is created dynamically here. Therefore, when the queue object goes out of scope, the destructor simply deallocates the memory occupied by the array that stores the queue element. The definition of the function to implement the destructor, which is our next thing to do, is basically nothing but to delete the list that we already generated. So what I need to do there is to delete the list, and there you go. After that, it is simply destructed and gone. So the implementation of copy constructor and overloading assignment operators are left to you as an exercise to do. Remember, the definition of these functions are absolutely similar to those we discussed for LinkedIn and a stack, so that's the same thing. So you can easily do it right there. Because the size of the array stored the queue elements is fixed, only a finite number of queue elements can be stored in the array. Also, the array implementation of the queue requires the array to be treated in a special way together with the values of the indices queue front and queue rear. The linked implementation of a queue simplifies many of these special cases for the array implementation, and because the memory to store a queue element is allocated dynamically, the queue is never full. This part of the video basically quickly goes over the linked implementation of a queue. Remember, because elements are added at one end and removed from the other end, we need to know the front of the queue and the rear of the queue. Thus, we need 2 pointers, queue front and queue reader, to maintain the queue. Now let's take a quick look on the code that actually abstracts this implementation, which is pretty similar to what we did for the array implementation of it. Before we actually look at the code itself, let's just quickly review the fact that linked implementation of a queue is absolutely similar to implementation of a linked list created in a forward manner, in a sense that add queue is similar to insert first, initialize queue is like initialize list, is empty queue is similar to is empty list, delete queue can be implemented as before, queue front is the same as first, and queue rear is the same as last. So when it comes to the code, the definition of our node is going to be very similar to what we did in the past. There is going to be a information type and there is going to be a pointer over there. And then we're going to have the operator overloading portion that we want to overload the assignment operator. We have the isEmpty queue, which is the function to determine whether the queue is empty. And as we said, like before, the post condition returns true if the queue is empty and otherwise returns false. We have the isFullQueue, which is the function to determine whether the queue is full or not. The post conditions are exactly as the ones that we used to have before. We will have the Initialize Queue, which is the function to initialize the queue to an empty space. Again, post conditions are exactly like what we now discussed for the array-based implementation of the queue. We have the front, we have the back, no changes over there. They will act exactly the same. We have add queue, delete queue, and we have the default constructor, copy constructor, and destructor to go in there. The private members we're going to use are the queue front pointer and the queue rear pointer. And as you can guess, pretty much same thing as when we implemented a linked list.